Hey you guys, welcome back to the channel PHYSICSSIRJEE. We are in Pathfinder Solution series and I have brought forward to you a very important concept through the problems of Pathfinder, right, which is going to be solved using the optical path concept. Okay, so I'll be taking up 3 problems in that book which cater to this particular concept. Okay, so we'll try to first of all go through the required understanding of that concept before we jump into the problem solving of the ones that I have put on the thumbnail. You could see we are going to do the build up your understanding 30 and build up your understanding 31 and check your understanding 8th question. Okay, so let's move forward. So let's first of all read the question, try to understand what he's requesting, and then we'll go into the concept. Okay, so a transparent rectangular slab of length L equal to 20 centimeter, this one, and thickness D is equal to 4 centimeter is placed in front of a converging lens of focal length 20 centimeters. A screen S is placed in the focal plane of the lens. The refractive index of the slab of material linearly varies from 1.5 at the bottom and increases by an amount of delta mu is equal to 2 into 10 power minus 4 by the time it reaches the top. Okay, so there's a mu which is variable in this y direction. Okay, and a parallel beam is made to be incident on this particular slab, and what kind of pattern appears on the screen is the question. Okay, so the thing is, in this type of questions where the slab's variation of refractive index is given, you should not assume that there is only one ray by ray and all the rays will just go through straight. Ray is a mathematical construct, and whenever variable refractive index is taken into account, you need to attempt these kind of problems using the concept of wavefronts and also the optical path. So in order to understand this better, let's first go through the basics of optical path. Okay, now on the right side of the picture you could see there is a simplistic situation of a point source giving out light. Okay, so the rays are also drawn and also wave fronts are also shown in the same diagram, and once they are getting refracted through this convex lens, they form an image. This we learn in ray optics. How do you understand the same thing using wave optics? Okay, so the logic is whenever this point source gives out rays, we can understand that it gives out waves of electric field impulses, right? Electromagnetic waves. So they do have certain functions according to Maxwell equations like E naught into sine of omega t minus k, R1, R2, R3, all different directions it's going. So each direction I can designate it as some R direction and I should be able to write an equation. Okay, so once we write sine of omega t minus kx, we can discuss a phase for that particular function. So all the points, once they start traveling, assuming all of this is air, they start traveling to certain position, they maintain that phase that they had at the start. Okay, so if you collect all the points which have the same phase after some time t and after traveling a distance x or r, then joining all of them in an imaginary situation gives you a surface which is known as wavefront. So all points on a wavefront are of same phase is the understanding. Same logic is even stated in Huygens wave principle, where you don't have any equations, you just assume that they are all in same phase. Points and wavefronts originating in phase from the source should culminate at the image in the same phase. How is the image formed? You should understand that all these wavefronts are this electrical pulses that you are traveling with certain phase, they get refracted, and all of these simultaneously, if they reach that point, then only a sensation of image is created. That in phase interference should happen. Okay, right. So this phase can be explained in 2 ways. One is the concept of optical path, which also embeds the Fermat's principle. Another alternative and slightly less famous way is to understand it through this particular equation. So we'll start from here and then go to this place. Okay, now take one particular comparison between the straight ray here. Can you see there is a straight ray, label it as 1, and then there is a slightly non-straight ray which actually gets refracted and then goes down. So I've depicted those two in these 2 paths. Okay, so from source, which is point A, there is a straight ray reaching B, which is the image, and then there is a slightly larger path it is traveling. Now I have represented the electrical wave with some electrical vibrations like this, which can be written as E equal to E naught into sine of omega t minus kr in both the directions. Okay, this one has R1 direction, this one has R2 direction. Okay, now if the rays start at A, travel through different distances. Now geometrically these distances are different, but they should reach finally simultaneously at this place, which means that greater distances obviously are supposed to be traveled by lesser average speeds. The speeds are all not the same throughout. Average speed here and average speed here are not the same. And which of these two terms will differentiate these two paths? Please understand, since time is simultaneous and frequency doesn't change with medium, this omega t term for this two travels will be the same. It is the kr that actually differentiates these two travels. So if the simultaneity has to be maintained at this place for all these rays, then the value of average value of k1 r1 of this and average value of k2 r2 of this should be equal to each other. I hope you understood up till this point. So let's concentrate only on this part. Now, so if they have to travel, start at A and travel through distance, different values of R, and finally reach B simultaneously to form an image, the K1 R1 along path 1 and K2 R2 along path 2 should be same. Why is that? Because this entire thing is called phase, and the idea of wavefronts is to have the same phase, then only image would be formed here. So what is angular wave number? K is angular wave number. You can write 2 pi by lambda 1 and this is 2 pi by lambda 2. I'm writing all average values. Please understand, each you should actually write K1 dr1, K2 K1 dr1, all this dr2 dr2 dr2s you add. So I've integrated all that stuff and then writing this particular part. Okay. Now, therefore, lambda is nothing but velocity divided by frequency that I have substituted here. The frequency is medium independent, so I get it cancelled. And velocity of light in any medium can be written as c divided by mu of that medium. Okay, so from here, if you come to this point, c can get cancelled, and you end up having a important understanding that if two rays travel or two wavefronts travel in different media, then if they have to meet simultaneously at that place, then they're not geometrical paths are not supposed to be equal. Some term that you are getting are equal. This term, therefore, we come back and define it as the optical path. So actually, when you equate optical path, you are actually equating the time taken from one place to another place. That simultaneous idea is embedded in the idea of the optical path. So in order to talk about equal time travel, we define something called as mu times r, which is the optical path. So we all say that going back, the optical geometrical paths of different rays, can you see, are different, but because this is thick at the middle and thin at the top, the optical path calculations would be same for all of this. Then only you'll be talking about the image. So this is the basic understanding of why we always define optical path. So finally, what we conclude, the path length light would have traveled in vacuum in equal time is defined as the optical path. If R1 is traveled in the medium mu1, then in the same time mu1 R1 would be traveled by that particular ray in vacuum. So that is the basic understanding of optical path. Okay, right? So let's move ahead to the question now, that question number 30 that I spoke of. You sent rays like this and mu was varying in this direction. Okay, so here it was 1.5, and by the time it reached the top, right, so like this, the mu is decreasing. Okay, sorry, he said increasing in this direction, and here the mu is slightly more than the mu at the bottom. Let's call it as mu plus delta mu. Now you realize that if I have a wavefront here, different points on that wavefront start out with the same phase. Since at the bottom mu is lower, it will travel faster in a given time. In the same simultaneous time event, because mu is larger here, it will travel a lesser distance. Okay, right? Optical path of the top and bottom is the same, geometrical paths are different. So in between also you can, because there's a linear variation, all these points reach the ends of some point where you join them, that is called the wavefront. So wavefront, which at the start would have been straight like this, it would get tilted by the time it reaches here. So you can always calculate that particular angle. Therefore, instead of rays coming straight out, they should be drawn perpendicular to this so-called wavefront, blue color wavefront, and therefore rays will make an angle which is same as this theta. Can you see? This is theta. This should be also theta. Okay, right. So if you can get this value of theta, then you can understand that any parallel beam which is inclined to the principal axis will actually get focused in the, not at the focus, but in the focal plane. You can just join this line and this is where it gets focused. So you can get this y if you can get this theta, and if you want to get this theta, you need to talk about an optical path idea in this small triangle. Okay, so the time taken or the optical path for this but time is same as optical path. Now I hope you understand that. So I should be able to equate optical path of this L and optical path of this L prime should be the same so that I can form a wavefront. And that's what I have written. Equating optical path lengths of the bottom and top ray, mu L at the bottom should be equal to mu plus delta mu into L prime at the top. Okay, so you can get the value of L prime. And what is this triangle? The small triangle, this distance is L minus L prime at the top, and this distance is D. Since this is very small variation delta mu, this angle also will be very small, so I have written tan theta as theta. Okay, so you get this particular number, and theta therefore can be written as delta mu into L divided by D by substituting this value of L prime. Once you get the theta, I think you are ready with y. Y is f times theta. I just substituted this. So there won't be any pattern. There'll be simple one single spot at this place in the focal plane at a certain deviation. This deviation is calculated from here. I hope you appreciate this. Let's move on. Stay back. I'll give you a practice problem also at the end. So 31, to build up your understanding, refractive index of material can be adjusted by diffusing impurities. Moreover, by adjusting concentration distribution of diffused impurities, a specimen of any desired gradient of refractive index can be obtained. Consider a thin disk of uniform thickness D made of a transparent material, refractive index of which is made to vary with distance r from its center by suitable diffusion of impurities. Lot of language. I'll tell you what he's doing. From this particular point in the radial, this is a disk, you're seeing a side view, this distance is D, the radius is not visible in this. So from the center to the radially outward positions, the refractive index is being changed. That's what this entire drama is all about. If the parallel beam of light incident normally on this, now as I said in the previous problem, mu is variable, so you should use wavefront theory and not the straight rays. You should not say all the rays will come out simultaneously. Okay, right? So they are supposed to, it seems, converge, because maybe we are guessing that the wavefronts are going to get tilted. You end up getting convergence, it seems. Okay, right? So what should be the suitable expression for the radial variation of mu? If this is at a distance small r, mu should be, it seems, function of r such that the focus can be obtained. Okay, so that's the question. Assume refractive index at the center is mu naught. He wants mu as a function of small r distance. Okay, right? So let's go ahead with the solution of this, again using the concept of optical path. Now I've drawn only two rays, like what I did in the conceptual understanding. If I have to believe that there is an image or a focus point, then the ray that is traveling straight from the center and the ray that is traveling from the top, they should meet simultaneously, which means they should, simultaneous means not same geometry but same optical path. Okay, at a distance smaller from the center of the disk. Now you could see that if I keep drawing wavefronts like this, okay, right, they will simultaneously travel up till this place. The difference starts once they enter this region. Okay, so I have put the yellow dots here so that I can tell you the difference. Now since the refractive index is larger here, this will actually travel slower. So by the time this blue one travels to this position, this one would have come out already. Okay, so, and because it has to travel a greater distance, this will travel faster in this medium. So the logic is, from this point the red optical path, and from this point the blue optical path should be again the same. It's the same logic that I have been telling, right? So equating optical paths for the two different points traveling on the same wavefront reaching I. So this is one point reaching I, this is another point reaching I. The wavefronts will get tilted like this. Okay, so they actually will get tilted in a curvilinear manner because I have to draw many more in between also. Okay, so the blue one starting from here travels this D in mu naught and then travels this F in air. So simple, 1 into F. Whereas the red one travels in here, the variation we don't know, I wrote it as mu, which could be a function, into D. And once it is out in the air, it travels this root of r square plus x f square. Okay, right? So rearrange, he wants mu as a function of r. So I rearranged it. Okay, so took f by d common. He already said that the value of r is very small compared to f in the question. You could see that here. Assume the value of f is very, very large compared to r is very small. So that gives me a chance to use the binomial approximation. Okay, so this is very simple now. 1 plus r square by f square whole power half, 1 plus x whole power n is 1 plus nx if x is very small compared to 1. I've used that here. The ones get cancelled after binomial approximation, and then therefore you end up having this relation becoming this. So mu as a function of mu naught and r comes out to be a decreasing function as expected in the upward direction, but it comes out to be a simple quadratic relation for small values of r. Okay, right? So that's an interesting idea. Then third question, which is even more challenging. This is from Check Your Understanding section, problem number 8. Refractive index mu of an atmosphere around a planet varies with altitude h according to the equation given. Okay, so there is a spherical planet, and as you climb into the atmosphere at a height h from the surface, the refractive index is actually decreasing, as you could see. Denoting radius of the planet by capital R, find the altitude at which a point of flash of light spreads around the planet in a spherical layer concentric with the planet in addition to other directions. Okay, right? So let's try to understand what he's trying to do in this particular question. Okay, so right, concentrate on this particular diagram first. We'll discuss that. So this is the planet according to me, and someone has put a flash of light towards right at this topmost point at some height h. Okay, now this flash of light, if this was vacuum, would have gone straight like this. Since there is a variation in the refractive index as a function of height, the top point of that flashlight, remember flashlight is a beam, and beam always has a width. You cannot take beam as a ray. So I have drawn, that's why, the red colored thing with certain thickness. So let me zoom into you that particular diagram to show you that thickness. So this is the thickness I am talking about. So what I argue is this this point and the topmost point are initially in the same phase. Imagine someone has put the beam towards right. Now, since this point is under the action of a different refractive index, and this point, which is slightly away, let's call it as dh height. Okay, this width is dh height. This is actually going to have a different refractive index. Okay, now thing is, in order to travel certain distance, remember optical path should be same. This is going to travel here, and this one slightly curves in order to come to this position. Now if it has to come in a circular manner, remember in this has to completely circulate around according to the problem, then if I join the 2 points again to form the new wavefront, remember this yellow one is the old wavefront and this one, and if I extend it back, then it should pass through the center. Then only I can call it a circular thing. Remember, he also said it's spherical because the flashlight starting from here, if I throw it towards right, it will come out this way. You can throw it out of the screen, then it will have a circle like this. Just imagine you throw it in all directions, it forms a sphere of this thing. So we are only solving it in one plane. So when can this happen is the question that we are going to ask ourselves. So just concentrate on the bottommost point traveling this arc distance and the topmost point traveling this arc distance. In order to call themselves a wavefront, even though they are going to travel slightly different geometrical paths, they should travel the same optical path. Okay, so this particular part of the diagram, I'll zoom and draw it for your understanding. Okay, so imagine I zoomed that out. Can you see this one? The top point of that laser and the bottom point of that laser flashlight, right? Separated by how much distance I said? DH, okay? And this distance from the center should be R plus H because altitude is H, the radius is given as R. Now, since that arc, because of small angle, can be almost considered to be a straight line there, okay? So this bottommost point, if it travels this geometry path, and this topmost point travels with this geometry path, okay, right, then the wavefront that is formed after joining them after dt seconds should again pass through the center. Then only it will keep curving like this. Okay, right? So what should I equate? Are these two path lengths same? No. Are these two optical path lengths same? Answer is yes. That's how the simultaneity works. So the bottom and top of the flashlight should travel same optical path to be part of the same wavefront. Okay, so at the bottom, I would say the mu is a function of h, right, and multiplied by this distance. What is this distance? The arc length, right? The distance r plus h into d theta. That's what I've written. So optical path is mu into length. Length itself is radius into angle. Similarly, on the topmost point, obviously the mu as a function should be h plus dh function. and the distance also will become r plus h plus dh into same angle will be same, right? Angle gets cancelled, and you end up having, imagine this left hand side, I call it as function of h. Then the above equation will imply, what is this going to be? It will be function of h plus dh. So if this is f of h, then this is f of h plus dh. This equation is telling us to assume a position of h where f of h is equal to f of h plus dh. From the first principles of differentiation, remember, when will this happen? When f dash h is equal to 0. I think, how do you write first principles of f dash h? You'll say limit delta h tending to 0, f of h plus delta h minus f of h divided by delta h. I hope you are better math students than me, right? So you should be able to recognize that this will automatically imply this. So go back and ask yourself, you are supposed to find out a place where the differentiation of this left hand side equal to 0. What is mu as a function of h he gave? Mu naught minus kh. It was linearly decreasing, multiplied by r plus h. I want that to be equal to 0. I forgot to write a equal to 0, so let me put that one out for you. This equal to 0, when I differentiate and equate it to 0, then I end up getting the required altitude at which this is going to happen. So you choose this particular distance and put a flashlight in all directions tangentially at that place, even out of the screen. All of them brilliantly go around and form a sphere of light, which I showed it as a circle in one plane. Okay, there is a very good practice problem that you should take up from 200 more puzzling problems book, problem number 119. Similar problem, okay, but there is a small difference. The variation has been changed. Can you see there? The variation was linear. Here it is not linear. The denominator is changing with height. So here, curiously, he says any laser beam directed horizontally at any arbitrary altitude. In our problem, there is only one particular height at which that special phenomena happens. Here he's claiming that at any altitude it follows or circles the planet. For that to happen, from the given information, you are supposed to find the radius of planet. I absolutely love this problem because the book gives 3 solutions, of which one is based on Huygens wave principles, second one is the Fermat's principle, and third one is based on the TIR. And you could say fourth one is approximately my solution, which is not given in the book. So if you go through this video and solve this problem and go through all those 3 solutions, which are actually interconnected, it's not like there are 3 independent principles. Okay, I have given you the electromagnetic wave principle idea also of the phase. This should be a complete analysis of your understanding of optical path principle. Okay, so please make sure you go through all the 3 solutions of this problem after the attempt. Okay, I hope you loved the way the optical path concept is presented to you, and we have, as a bonus, solved 3 problems of Pathfinder solution series. Along with that, please, if you like the other want to check out the other series, there are 3 more series going on, as you could see on the screen. The links of the playlists are in the description below. Please do go through them, and if you like this particular presentation, do like it, share it, and subscribe to my channel. And please request your friends and others who can benefit from the channel to subscribe and let me grow the channel much more. Okay, so thank you very much, and see you in the next video.